We are almost done with this section. The last thing that we need to talk about are infinite limits and vertical asymptotes. So taking a look at the function we have on the screen, we're going to call that h of x. This is one of the first functions we saw at the beginning of the section. This function is undefined at x equals 2. We can see that because the function graph, pretend that's a straight line. The function graph never crosses the x value at 2. If we wanted to talk about what the function is approaching as x gets closer and closer to 2, we could look at our one-sided limits. From the left of 2, as we're traveling along the function, we can see that the function output is getting bigger and bigger and bigger. It's just getting out of control. It's going up and it never stops. And there's no reason for it to stop. It's going up to infinity. So the left-sided limit is sending us up towards infinity. And if we look at the right side, we see a perfect identical infinite limit. So for this function, we can see that as the x values are narrowing in on x equals 2, the function values are going up to infinity. So we call this an infinite limit. Now, if we look at what the definition of the function is for h of x, we see this rational expression. Remember, rational expressions are basically fractions where the numerator or numerator or denominator could be a polynomial. In this case, it's our denominator. This denominator is a polynomial. In fact, it's a binomial squared. So what we need to do to find a vertical asymptote is take our denominator and set it equal to 0. Creating this equation will help us find the asymptote, specifically the vertical asymptote. So we can square root both sides to get rid of the exponent of 2 on the left side. So now we have x minus 2 equals the square root of 0, which is just 0. We can add 2 to both sides so that we have x all by itself on the left and positive 2 on the right. This tells us the equation of our vertical asymptote. That's exactly the x equals 2 line that I drew when we first started this video. So functions that have vertical asymptotes will have infinite limits. In this case, both the left side of the vertical asymptote and the right side of the vertical asymptote went all the way up to infinity. But that's not always true. Let's take a look at this function. We're looking at the function 1 over x, and we're trying to evaluate the limit using a table of values, and then we're going to use a graph to confirm our conclusion. First thing we need to do is remember what the table of functional values looks like. We need a bunch of x inputs near the limit that we're trying to evaluate. So we look over at our limit notation. Each one of these 3 limit expressions is talking about x approaching 0. So our table of values needs to center around 0 for the function 1 over x. We can make our table using calculator, GeoGebra, whatever you'd like. I've already got my table here on the screen. Notice that as we move down the table, I'm getting closer and closer to x equals 0 on the left. And then as I move down this table, I'm getting closer and closer to x equals 0, but I'm coming from the right. So the left side of 0, the numbers are smaller than 0. The right side of 0, the numbers are larger than 0. We plug all of these x values into our functions to get the f of x column values. And now we're ready to answer the questions about these limit problems. The first one I'm looking at says to allow x to approach 0 from the left. So we're going to use our left table. And we want to know what's happening to our function as x is getting closer to 0. Well, if we follow this trend, we're seeing that our numbers are increasing without bound in the negative direction. -10, -100, -1000, -10,000. It just gets really, really large, but negative. So that tells us that this limit is going to -infinity. Moving on to our next limit, we see that we're approaching 0, but from the right side, so we'll use our right table. And as x is getting closer to 0, our function values are growing without bound to +infinity. So 10 to 100 to 1,000 to 10,000, it just gets bigger and bigger. We know that that limit is going to +infinity. Now we have our left-sided limit equal to -infinity. Our right-sided limit is equal to +infinity. This last limit down here, this is our two-sided limit. In order for the two-sided limit to exist, the left limit and the right limit have to match. And although these might look similar, one of them's negative, one of them's positive, they are not equal. Therefore, this two-sided limit does not exist. I have the graph of that function on the screen. I've typed in f of x equals 1 over x, and GeoGebra has graphed that for us. And we can see that this is quite different than the last function that we saw, because one side of the function is going down to -infinity, and the other side of the function is going up to +infinity. And so we can see that this is not like the green function that we first saw. We have one side going up, one side going down. This leads us to a question about a pattern. And in fact, there is a pattern. Theorem 2.3 points out this pattern. It says that if you have a rational expression of the form 1 over x minus a raised to the nth power, then we have two possibilities. One possibility is that that exponent is even. If the exponent is even, both sides are going to point in the same direction. So either your function is coming up to +infinity from both sides, or if we had a negative function, then our values would both go down to -infinity. So we have two possibilities there within the even case. Or we have the odd case. If the exponent in the denominator is odd, then we have the case that we just looked at, where one side is going down to -infinity and the other side is going up to +infinity. Or it's possible that the roles were flipped. If we had a negative function, maybe coming from the left, we go up to +infinity, and from the right, we go down to -infinity. So in any case, if you have a rational expression, then you have a potential for an asymptote. If the exponent in the denominator is even, then the function is going to point in the same direction, no matter what side of the asymptote you're on. Or if that exponent is odd, then the function is going to go in opposite directions, depending on which side of the asymptote you're on. So even, the left and right limits match. Either they're both positive or they're both -infinity. Odd function, the left and the right limits are opposite. So if the right limit is +infinity, then the left limit needs to be -infinity. This is a pretty cool tool because we can quickly determine if we have a positive or negative infinity limit just by looking at the form of the function. So we are looking at a definition here that tells us that if you have a function with a vertical asymptote at x equals a, then the limits around that a either have to be positive or negative infinity on the left, they could be the same or opposite on the right, or they both have to go together, and that would give us our two-sided limit. So let's take a look at some of the functions that we have here. If our function is 1 over x plus 3 raised to the 4th power, then our exponent is the 4, which is even. Even functions behave in the same way. So they're both going up to positive infinity, or they're both going down to negative infinity. And I see a small typo in my function. I have a plus. So let me fix that in these notations down here. If we're traveling from the left, we're plugging in numbers that are smaller than 3. When we add them to 3, raise them to the 4th power, we get a positive number that comes out of this. And as we get closer and closer to 3, we're getting closer and closer to positive infinity. If we're coming from the right, then we're adding a number that's larger than 3. Then we raise it to the 4th power. Again, we're going to have a positive infinity limit. I know it's not negative because nothing in here contributes to a negative value. Notice that these two things match. The left limit and the right limit match. Our theorem says that has to be the case because our exponent is an even number. If these two things are equal to each other, then they must also equal the two-sided limit. So our two-sided limit would have to be positive infinity as well. Let's try another one of these vertical asymptote limit problems. This time we're looking at the function 1 over x minus 4 to the 5th power. Our exponent is 5, which is an odd number. So we know that we either have a picture that looks like this around our asymptote, or we have a picture that looks like this around our asymptote. Because we have x minus 4 in the denominator, we know that our asymptote is going to happen at x equals positive 4. That's important because knowing that that's the asymptote is going to help us solve these limit expressions. Let's take a look at our left-sided limit first. If I'm looking at x equals 4, and I want to compute the limit coming from the left, then I want to use numbers that are slightly smaller than 4, like 3.9, for example. 3.9 is to the left of 4. It's very close to 4. And if I stick that inside of my function, I can see what types of values my function spits out to the left of 4. 3.9 minus 4 in my denominator is going to leave me with a negative 0.1 raised to the 5th power. Now remember that odd exponents will spit out negatives. Negative 1 squared comes out as a positive number, but negative 1 cubed, an odd exponent, comes out as a negative number. So I know this expression, 1 over negative 0.1 to the 5th power, that's going to be a negative number. Now I could type that into a calculator and find out what it is, but really my goal here was to figure out if I'm getting positive numbers to the left of my asymptote or negative numbers. And we can see that this is the situation that we're dealing with because to the left of our asymptote, our function is negative. So we know the left limit is going to be negative infinity. Our exponent is odd, so the right limit would have to be the opposite. If the left limit is negative infinity, the right limit has to be positive infinity. And if the left and the right limits don't match each other, then we know the two-sided limit does not exist. In this section, we talked a lot about limits. We used tables to compute limits. We used graphs to compute limits. We talked about limits at discontinuities, vertical asymptotes. There's a lot in this section, so take your time, make sure that you digest all this material. But one of my favorite questions in this section is to give you a picture of a graph, a really wild graph, and then to ask you from the graph to tell me what certain limit values are. So here's an example of that. This problem tells us to use the graph to determine each of the following. So we have 1, 2, 3, 4 things to calculate, and we want to do those 4 things for the various a values that are given. So let's start with a is equal to -4. That means the limit is going to -4 from the left in the first expression. The limit is going to -4 in the right in the second expression. The limit is going to -4 from both sides in this third expression. And then lastly, we want to evaluate what the function is at -4. So my first suggestion would be to draw on the graph the x equals -4 dashed line. So we have that on our graph, and now we can start to answer the questions. The limit from the left, that's what the first expression says. That says travel along your function until you reach that dashed line, and then tell me where you're headed. If we're heading towards that dashed line, it looks like we're right at the x-axis, so that limit's approaching 0. If we're coming from the right, then we're traveling on the function from the right, again heading towards the x-axis, so that limit is 0. If the left and the right limits match, then the two-sided limit is also equal to the same thing, 0. And then lastly, we want to know what the function is equal to at x equals -4. So I'm going to clean up my picture here. At x equals -4, this is the point on the curve. That's right on the x-axis. So our function output has to be equal to 0. For any continuous function, a nice smooth function without any missing parts, without any jumps, or any kind of weird stuff going on, all 4 of these things should match. But when you start to throw in missing pieces or jumps, then all bets are off. So let's take a look at some of the other a values. Now let's look at a is equal to -2. So that means we're looking at our left limit, right limit, two-sided limit, and function value when x is equal to -2. So we'll draw our x equals -2 vertical dashed line. Coming from the left, traveling on our function, it looks like we're approaching 3. Now our function is not defined right there, but that's okay. The limit is taking us towards the output 3. So from the left, we're going towards 3. If we're coming from the right, staying close to our x equals -2, but coming from the right, we also are approaching that y value at 3. Left and the right limits match each other, therefore the two-sided limit matches. They're all equal to 3. Lastly, we need to decide what the function value is at x equals -2. This open circle says the function is not defined at that point. There's no closed circles anywhere on the x equals -2 vertical line. So we know this function is not defined here. Now, if there had been a closed circle above that open circle, then we would say the function definition matches that y value. But that doesn't exist, so it's undefined there. Now let's look at some more complicated stuff. What about when x is equal to +1? We draw our vertical our vertical line at x equals 1. Coming from the left, traveling on this function, coming from the left, looks like we're heading towards the y value 6. Coming from the right, I'm not going to start from way over here unless you really want to, because I'd have to jump over this asymptote. So we want to stay close to +1. So we're going to travel on this, coming from the right. This looks like we're heading towards 3. The left limit is taking us towards 6. The right limit is taking us towards 3. Because the left and the right limits do not match, we know the two-sided limit does not exist. We have one last thing to answer for this a value, and that is, what is the function defined to be at +1? On our dashed line, there's 2 spots that hit the green dashed line. One of them is an open circle. That means the function is not defined there. One of them is a closed circle. That is the function's defined point. So at x equals 1, the function is defined to be 6. We have one last a value, and that's 3. So at x equals 3, we draw our vertical line, which is a vertical asymptote for this graph. Looking at the limit coming from the left, we can see that our values keep getting smaller and more negative. So we know the left limit is negative infinity. We can see that coming from the right, we have that same trend. We're going down, down, down to negative infinity. So the right limit is also negative infinity. Since the left and the right limits match, we know the two-sided limit is also negative infinity. Lastly, we need to define the function value at 3. Remember that I said this is a vertical asymptote. Vertical asymptotes happen when you have rational functions with a denominator that is equal to 0 at that asymptote. We're not allowed to divide by 0, and then whenever we try, we say it's undefined. So this function, although the left limit matches the right limit, therefore telling us the two-sided limit is negative infinity, the function is actually not defined there. Just like what happened at the negative 2x value. Two completely different visual scenarios, but kind of the same relationship between the one-sided, two-sided limits and function definition. All right, that's it for section 2.2. I hope you enjoyed the videos, and I'll see you later.